So far, we have discussed on the single stage impulse turbine and related performance parameters like blade efficiency, power output, power developed, then stage efficiency, nozzle efficiency, etc. And the condition for maximum efficiency, optimum blade speed ratio we have seen. Now, today we will see the multi-staging of the impulse turbine, as we know that there is difficulty with the single stage because all the power of the all the energy of the steam will be converted into kinetic energy, and therefore that kinetic energy must be transferred. That means all of the available kinetic energy, that part of that can be or should be transferred or must be transferred to the rotating wheel or the moving blade to maximize the efficiency. But the difficulty is that the in that case the blade speed or the rotor speed will be very high, of the order of 30,000 RPM. Okay, so to avoid that, because none of the device need to rotate at that speed, therefore definitely we need to reduce the speed by some reducing mechanism like gearing mechanism. We have to reduce, even if we produce the speed with we produce the power with a single stage impulse turbine. But again, there is a high carryover loss at the exit because there will be unutilized energy from the steam. Therefore, there is a necessity of using the power of steam in stages or in more than one stages, rather than using that or converting the steam energy to the rotor energy in a single stage. So we have to understand the necessity of this. I will suggest you that there is a good write-up in the Wikipedia section of the compounding of turbine. There it is very well written in within say 5 to 6 sentences what is the necessity of compounding. So that will give you a clear idea about compounding. So simply type the compounding of steam turbine in the Wikipedia page. That will give you a clear idea about say 5, 6 sentences. It is there. Okay. Now, therefore, we will see the multi-staging of the impulse turbine. We have already seen the multi-staging in terms of the velocity compounding and the pressure compounding on the first or the second class, when we were discussing on the different compounding principles. Okay, now we will see these again, and we will try to analyze the performance parameters for these. Okay. Now, so far, we have discussed all these performance parameters. Now, we will see the performance for a velocity compounded impulse turbine. Now, as we know that for a velocity compounded impulse turbine, there will be basically a single row of wheel, and on that there will be a single wheel, and there will be rows of basically moving blades. So that are called a, a two-row wheel or a three-row wheel that we have seen in the second class of impulse turbine. Just to remind you, the velocity compounded impulse turbine, I'm showing it. So this is a velocity compounded impulse turbine where this is a single row. So this is a wheel, single wheel, and on this you have this red one, the first red one, it is the first row of moving blade. Then the second set of double tick, double red tick, that is the single row of the moving blade, and this is the third row of moving blade. And in between we have basically two rows of stator, that is guide blades or guide vanes. So this is the three-row wheel. You can have two-row wheels also, as we have seen, as we have discussed, that a two-row wheel is more efficient than three-row wheel. Therefore, uh, two-row wheels are in general used. So again, we have seen that in a pressure velocity compounded impulse turbine, we generally used two such two-row wheels, and in between, that means these are individually velocity compounding, and again there is a pressure compounding. Okay, so both are done here. So these are nozzles basically. So nozzle, as we have two nozzles, there are two pressure compounding, and then each these are velocity compounding. Now we will discuss on the velocity compounding, velocity compounded impulse turbine and the print and the performance parameters. Okay, so for velocity compounded impulse turbine, uh, the the thing is that, so this is one stage, first stage. Now, what is the velocity compounded impulse turbine? Basically, that in case of the velocity compounded impulse turbine, we have basically there is only one pressure drop, and the velocity is uh, changed twice. Okay, so as we have seen, let me again show it. Velocity compounded impulse turbine. This is this one. So the pressure is reduced only once, and velocity is reduced in all moving blades. So in all the moving blades, the velocities are reduced, and in the guide blades, there is no change of velocity. This velocity change that is shown here, it is due to the friction only, due to other mechanical reasons or energy conversion related things. There is no velocity change in the moving blades. So only velocity change that is happening in the, sorry, there is no velocity change in the guide blades, only it changes the direction. So kinetic energy does not change. There is a small change due to friction, that is another thing. But whatever change is taking place, that is taking place within the moving blade itself. So it is a three-row wheel, so there are three velocity changes. So velocity change is taking place in compounded manner, or in breakups, or in stages. Uh, for this velocity compounded impulse turbine, we will see that this is the velocity diagram, or the combined velocity diagram rather, in the first stage, or for the first stage. And similar combined velocity diagram, combined velocity diagram means basically the velocity diagram at the inlet of the blade and at the exit of the blade. So velocity triangles are drawn at the inlet to the blade and exit from the blade, and then they are combined for the same blade velocity as the base of that triangle, of these two triangles, and then they form a combined velocity triangle like this. So they are basically combined. Now basically this is rotated, as you can understand. So I'm sorry, this is
নিচের দিকে তো করা যাবে।
হ্যাঁ হ্যাঁ করা যাবে। Actually, this is shifted obviously, because when you have a combination, so basically what it what you do is basically like this. So if this is the blade, I'm sorry, if you rotate it, okay, no problem. So here it is shown like this, shown like this. So now you can take, say the blade will rotate in this direction. Blade will move in this direction, and velocity to the steam will come in this direction, and therefore means if you rotate it up further like that. So this is tangential to the blade, and therefore the actual velocity, that is absolute velocity, will be like this. So this is the inlet velocity triangle, and similar triangle can be drawn at the exit also. You take the same value of velocity at the exit, blade velocity, and then uh, inlet exit velocity from the blade, it is tangential to the blade like this. So if they are basically beta 1 and beta 2 are same, it may be like this. And then the absolute velocity will be, so absolute velocity should be, so if you basically move it, so if you move it here, or if you move the steam velocity, that is relative velocity, either of them you have to move. In that case, it will be basically, so it is here. So it is like this. Now you can basically combine these two to get the basically uh, combined velocity triangle or velocity diagram. So it will be like this. For the same, you have the blade velocity here, and then this is basically same, and then parallel to this you can draw it here. I'm trying to draw as proper as possible. I think it's okay. this one, and then this one will be on this side. And therefore it will be here. So this is the combined velocity triangle we have drawn. For the sake of analysis, definitely you can uh, enlarge it. For the sake of analysis, you can enlarge it proportionately, and it will be like this. So this is the combined velocity triangle. This is U, and this is basically VR1. I'm sorry, VR VR1. I'm sorry, VR2, VR1, and then V1, V2. Like this, you can write. So this will be alpha 1, this will be beta 1, this is alpha 2, and this is beta 2. Okay. So that is the way to draw. But the thing is that for both the first stage and the second stage, if you have say two-stage turbine, that means if I can draw, or if we can draw the velocity triangles for two stages, then we can draw it for three-row wheel also, no problem. So the common thing that we have to understand first, that first row, what is that? In the first row, this is same as the single stage impulse turbine for the same thing. Only thing is that we have to understand the velocity is compounded. That means, so it is, I should write here, velocity compounded impulse turbine. Means basically two stages we are considering. For the analysis, it can be extended for n number of stages. So first stage, it is, you see the nomenclatures are extended, and at the end of this, we have added one index. For stage 1, it is 1 added. For stage 2, 2 will be added. So you see that here you see that VR1, after that there is another one. So up to VR1 it is inlet. One means for first one is for inlet, and second one for the stage 1. So V11, this is one for the inlet, and this one for the first stage. Similarly, VR2, this is at the exit of the blade, and this one is for the first stage. That means this VR21 is basically the blade relative velocity of the steam, with respect to the blade at the exit from the blade for the stage 1. And this is V21, that is absolute velocity of the steam at the exit from the blade for stage 1. So these last one, so if I just write here this last thing, say if I write say any quantity, say V, and then say some I and then J. So this I is for is it for the inlet or exit? For inlet or exit. So for inlet it is 1, for exit it is 2. And this J is for stage. That means stages. So first stage it is 1, second stage it is 2. So we can easily understand that. So these 1 is for all these are 1 for the first stage, even for beta 1 1, beta 2 1, alpha 1 1, alpha 2 1 for all these. And also there is delta V W1, that is the total wall component, change of wall component of the uh, steam. So that is total change, that is delta V W1 for the first stage. Now one thing that we have to keep in mind that this blade velocity will remain same for both the stages because they are connected to the same wheel. So here it is same wheel, even uh, in a say for example, if you have two wheels, they will be connected to the same shaft. Therefore, there will be same velocity. But here they are definitely they are going to be same because they are connected to the same wheel. So their velocity is same. You can refer to the figure and then you can understand that. So this is u, that is same. So that we have drawn. So for that we have to just refer this figure. This u is same for both the blades. They are connected to the same wheel. Okay. Now we have drawn the combined velocity diagram for the stage 1 and for the stage 2. And for both these stages, quantities are similar. Only thing, the nomenclature you will follow, and they are basically having a particular index for the particular stage and for inlet and exit accordingly. So here, just for clarity, I want to tell you. This is, you see that this is V22. That means what? That is absolute velocity from the exit of the blade for stage 2. Similar to that, all other quantities can be understood. Okay. Now, as we know, therefore, for this, what will be the work done, total work done for, say, for example, for these two stages, work done, we can write. So we can write here work done. Work done will be basically m dot multiplied by change in velocity. So for single stage, that was what? M dot into delta VW into U. So here it will be similar. So m dot into delta V. So it will be m dot into delta VW1 multiplied by U. And for the stage 2, it will be m dot into delta VW2 into U. Therefore, it is the sum of these two multiplied by U because they are rotating in the same direction. Therefore, the total work done will be addition of these two or summation of these two. That is the total work done. Okay. Now, another thing that you can calculate is the end thrust due to the axial movement of the axial movement of the steam. End thrust can be calculated as the difference in the axial component of velocity. As the fluid is moving, say, with this velocity, and the axial component of velocity is Vf1, say Vf1, and as the fluid is leaving the turbine, the axial component of velocity is say Vf2, then effectively the thrust that is given by the steam on the blade in the axial direction is due to delta Vf1, because that is the change, because at the inlet the steam is entering with Vf1, and at the exit of the blade it is leaving with some kinetic energy or some momentum in that direction. Therefore, effectively, the balance that is it has given on the wheel, that is different. That is the difference of this minus this. Okay, so that will be basically. So we can write end thrust due to the axial component of velocity, that is m dot multiplied by delta Vf1 plus delta Vf2 multiplied by u. So just let me explain one for that one blade. Try to understand that. Say for example, what is the axial component of that velocity? That it is going. So this one. So this is the axial component of velocity, that is basically Vf1. For stage 1, it will be Vf11 obviously. And what is the axial component of velocity at the exit? So this is Vf21. Okay. Now what is the meaning? That means when the steam enters the turbine, it came with Vf1, and when it leaves the turbine blade, moving blade, it leaves with Vf21. Therefore, the remaining, that means therefore whatever has been changed, that has been supplied, or that has been acted on the blade wheel. So therefore, that means uh, the remaining is the energy or the velocity with which the steam is leaving. Okay. So that is, therefore here it is coming with m dot into Vf, and then it is leaving with, so it will be m dot into delta Vf1, that is equal to m dot into Vf1 minus Vf2. Therefore, thrust is equal to that multiplied by that is the thrust. Sorry, so u will not be there. I'm sorry, u is not there here, because that is the force we are trying to calculate. Work done is energy, and this is only the force that we are talking about. So multiply, that is the momentum exchange with the blade in the axial direction. So that is the momentum exchange, the rate of momentum exchange on the blade in the axial direction. That is the end thrust. That means that is the momentum that it has already imparted, and it is leaving with the remaining momentum in the axial direction. So the balance or the difference that it has already transferred to the blade. Okay, is it clear? Now another thing is that for the End thrust. End thrust means basically when the steam is coming, it is coming with end thrust means basically axial thrust. So when the steam is coming, that is coming with m dot Vf1, and when it is leaving with m dot. So I was telling that end thrust basically means what? When the fluid is moving, that is actually giving a force in the axial direction due to its motion in the axial direction. So what is that force that the fluid is giving or applying on the axial direction? So when the fluid is moving, if the fluid has been fully stopped, that means if the axial velocity of the fluid has been fully stopped, then the total momentum that it would have given to the blade or the wheel is equal to m dot into delta f1, m dot into vf1, right? Because it was coming with vf1 velocity. Therefore, if the flow would have been stopped fully, then it would have been that full force would have been given to the wheel. So that is m dot multiplied by vf11. But as the fluid is not fully stopped and it is leaving with some velocity, therefore the effectively what is the force that is applied? That is this momentum minus this momentum, because the fluid is not leaving, the fluid is not fully stopped, it is leaving with some kinetic energy and momentum. Therefore the remaining momentum, that is m dot into f1 vf11 minus vf21, that is basically that has been applied to the wheel. So that is called the end thrust. M dot into delta vf1 is equal to end thrust. That is equal to m dot into vf1 minus m dot into vf2. Okay. Okay. Okay, sir. Okay. Okay. Now, another thing that can be calculated again for this, you can determine what is the blade efficiency, and therefore you can determine what is the optimum blade speed ratio. So that is blade efficiency you can define as the work done. This is work done on the blade, obviously, divided by the kinetic energy at the exit of the, or rate of work done or power. That is basically, this is rate of work done. This is rate of work done, obviously. Let me write properly. Rate of work done divided by this is rate of work done, that means power developed. This is rate of work done. So rate of work done divided by the rate of kinetic energy from the nozzle exit. Since you have only one nozzle here, so we know that is what. So if we have say two stages, then we can easily write that. So it is m dot multiplied by delta v w1 plus delta v w2 multiplied by capital U, that is the power developed, divided by m dot into v1. So it will be basically v11 square by 2. Okay. So accordingly, you can calculate what is that. So efficiency of the blade is equal to 2 delta V W1 plus delta V W2 multiplied by U divided by V11 square. Okay, this is the efficiency. Same as a single stage. Only thing we have added this. So that is the extra blade power that we are getting. Obviously, you see that for this blade velocity, this blade velocity will be definitely less. That you can understand. For a single stage, the blade velocity will be very high. So, but this delta VW1 and delta VW2, these are basically splitted and U is reduced. So that way it will be taken care of. So our target was to reduce the blade speed at very high speed of the blade by splitting the velocity. That means velocity of the blade, moving blade. That is called the velocity compounding. So that is the blade efficiency, and accordingly we can derive by doing that same mathematical thing. We will not do it again, but you can do it for maximum efficiency. What is the condition? And that can be done again for maximum efficiency. Efficiency we can derive the optimum blade speed ratio that is rho optimum to be equal to, here it will be cos alpha 11 by 2 into 2. Initially it was cos alpha 11 by 2. Now it will come to be cos alpha 11 by 2 into 2. It can be derived from this. Now, in general, for n number of stages, for n number of stages, the optimum blade speed is equal to cos alpha 11 by 2n. Simply it is number according to the number of stages. And also there is one uh, observation that work done, they are not basically same for all the stages. It is not equally distributed or evenly distributed or uniformly distributed. For the first stage, work done is more than the second stage. That is an observation. Okay. And in general, the first stage in a large turbine, the velocity or the pressure compounded impulse turbines are used. Okay. Next, we will see the pressure compounded impulse turbine. Somehow it is deleted. Now, for the pressure compounded impulse turbine, actually, what is there? As we know that for pressure compounded impulse turbine, basically there are a number of nozzles, and in all these nozzle stages, the pressure is reduced. That means there is expansion, and accordingly the velocity is increased. So that is the principle of pressure compounded impulse turbine. Okay, and what happens in the pressure compounded impulse turbine? For these, basically, that means all these are basically nozzles instead of that means guide blades. So these are basically nozzles. So let us see that, as we have seen in the first class or second class. This is pressure compounded impulse turbine. So you can see that these are nozzles instead of guide blades. So there basically expansion takes place and pressure reduces, and therefore velocity increases. And it is seen that the velocity at the inlet of the moving blade for all these stages are basically same, almost same. And here also, you see that the velocity due to the pressure reduction, after the pressure reduction, velocity increases, and at the entry to the moving blade, this is moving blade, this is moving blade. At the entry to the moving blade, the velocities are all same. Okay. So these are called basically the Ray-2 stages or Ray-2 turbine for the pressure compounded impulse turbine. And if we write the energy equation, so what happens basically, pressure drop takes place in more than one row of nozzles, right? Pressure pressure drop takes place in more than one row of the nozzles, and the increase in kinetic energy after each nozzle. There is basically, what is the necessity of pressure compounding? Pressure compounding is that you are basically doing a pressure reduction in a number of stages instead of a single stage. So therefore, the velocity rise will be within limits. So that is the objective. So the limits basically compounding are done for uh, getting the velocities within the limit or increasing the velocities within the limit. Okay. And for these pressure compounded impulse turbines, as we know that these are basically not high velocities are required. So in general, convergent nozzles are used. In case of D-level turbine, we have seen that basically convergent divergent nozzles were used in case of the D-level turbine. So convergent divergent nozzles were used. But in case of pressure compounded impulse turbine, in general, convergent nozzle are used, that you can see clearly. So these are basically convergent nozzle. So for convergent nozzle, as we know that maximum exit velocity can be uh, equal to only the sonic velocity, that is the for Mach number 1. So that is one condition that you have to keep in mind, that it is a convergent nozzle. তোমরা কম্প্রেসিবল ফ্লো পড়েছো তো? Compressible flow in the compressible flow that you have studied for nozzle, the maximum velocity at the exit from the nozzle of a convergent nozzle is the sonic velocity. It cannot be supersonic. So that I have explained in detail in our compressible flow lectures that you can listen. Yes. compressible flow টা পড়া হয়নি। আচ্ছা আচ্ছা। You can listen. There we have done extensively compressible flow lectures, both in Bengali as well as in English, as well as in Hindi. So we have done it, and that is that discussed. That I think in your syllabus also there is compressible flow. That is easy to understand. Only thing you have to follow the mathematical, yes, sir. Mathematical relations, thermodynamic relations, and that means different material conditions. For say, for example, isentropic flow of ideal gas. What will be the thermodynamic conditions? So these are there. It is not difficult. Okay. So in this regard, basically, so what we will basically define is pressure compounded. Quantities that we will basically define. One is called the carryover coefficient. It is the fraction of the kinetic energy corresponding to V2, which is available for utilization in the nozzle of the succeeding stage. So what is that carryover coefficient? It is the fraction of the kinetic energy corresponding to V2. which is available for utilization in the nozzles of the succeeding stage. That is called carryover coefficient. So fraction of the kinetic energy corresponding to V2. V2 means what? V2 means basically in a particular stage, V2 is the exiting velocity from the stage. So that is V2, right? Now, the fraction of the kinetic energy corresponding to V2. So what is the kinetic energy corresponding to V2? Say from V2 is the absolute velocity of the steam leaving stage 1. So kinetic energy is equal to, or rate of kinetic energy you can say, m dot into V2 square by 2. So phi is basically for the next stage, basically it will be, what will be the kinetic energy that will be there. So it is basically the fraction of that. For the next stage, say kinetic energy. Okay. So kinetic energy for the next stage is equal to basically phi multiplied by m dot V2 square by 2. Okay. That means what basically you see that, say at the exit from the nozzle, Okay. So here we see that this is the first stage. So in one stage, and then it is the second stage. So from that means the carryover coefficient means basically the fraction of the kinetic energy corresponding to V2. V2 means here, what is V2? Say for example, this is V1. This is V1 here, exit from the nozzle. And what is V2? This is V2. So fraction of the kinetic energy that is available for the utilization in the nozzle to the succeeding stage. So this is V2, fraction of that energy that is available for the next nozzle, fixed nozzle. So that is called the carryover coefficient. So this is V2 and this is V1. So therefore, the fraction of the kinetic energy that is available for the nozzle in the succeeding stage. So this is the expansion in the nozzle again, and again it will be from some velocity, it will be coming to V1. Right. So this will be V1 and this is V2. So if I write the energy equation, try to understand that this is V2 and this is V1. Though, so again it will be V1. So all the velocities are V1, right? And this is V2. So if we write the energy equation, energy balance, what will that be? Basically, at the inlet to the next stage, the efficiency will be basically, sorry, at the exit from that, at the exit from the next stage. So no, at the exit from the next stage of the nozzle. So it will be basically V1 square by 2 plus some H1 enthalpy is equal to V2 square by 2 from the at the inlet. V2 square by 2 plus H2. So this is at the exit from the next nozzle, and this is to the inlet to the next nozzle. Okay, let me bring that diagram here again, then it will be easy to follow. This one. Sorry. You see that here it is basically, say for example, if you take one stage, this is one stage. This is one stage. And this is the next stage. And this is the next stage. So what is happening? Here, for the first stage, the exit velocity is how much? This is V2. This is V2. So that is exit velocity. Now, therefore, that part of that is available at the entry to the nozzle. This is nothing but the nozzle. Okay, let me uh, enlarge it so it will be clear. Okay, now just follow it. So this is V2, V2, this is the nozzle, fixed nozzle. So this is the fixed nozzle. We color it, fixed nozzle. This is fixed nozzle. The same color I'm using. Now this is the fixed nozzle here. So V2 is the energy that is available here. Sorry, V2 is the energy, V2 is the velocity of the steam after passing through the moving blade. As we know, that is inlet to the blade is V1 and exit to the blade is V2. But here, this